everyone. This is How I Met Your Modem. Thank you all for coming. It's a great honor to be here at Hack in the Box 2013. And today we're going to talk about DSL devices. We're going to talk about its functionality, about vulnerabilities we found in these devices, and exploits we wrote for them. And we're also going to demonstrate a few, our setup here, and some of the exploits we wrote. Before we start, we would like to introduce ourselves. So, who are we? I'm Steven. I'm a software developer for a local software development company in the Netherlands. And in my own time I do a lot of security research. And I also like to produce electronic music. And I also play these so-called CTF, Capture the Flag games, with the Dutch Eindbazen CTF team, which Peter, my fellow speaker, is also part of.
So, hello, I'm Peter. I'm a software developer at a small hosting company in the town I live during the day. At night I'm a hacker, security researcher, reverse engineer, whatever you want to call it these days. I worked on the homebrew channel for Nintendo Wii. I'm part of the Hack in the Box CTF crew from the Netherlands. And yeah, I like computers, let's keep it at that. So, a small introduction. What is DSL modem? Why should we care about them? So, DSL modem is basically a device or appliance installed at the home of an end user in order to provide the end user with internet connectivity. So basically you hook up the DSL connection, plug in a bunch of computers or connect through the Wi-Fi using your laptop, and you should be able to surf the internet. So why should we care about them? Recently people have been focusing lots of energy on computer security. Most notably antivirus on desktop PCs, firewall appliances, servers should be secure, web servers should be secure. But nobody realizes that modems, switches and other network appliances are basically also computers that we can attack and own. So that's basically why we started doing this research. We wanted to find out more about these devices. Are they really that much of a black box? Can we easily attack them? And yeah, let's see what we can do. So over here we have a picture of a Geissler modem. It's more or less the same modem that we have here on stage. Not exactly the same model, but you get the idea. So basically on the far left you have a DSL connection where you plug in your DSL line. Then we have a couple of Ethernet ports, which are used for the computers on the local area network. So you hook up your laptop or your normal desktop computer here. Then they have a bunch of old school phone ports where you can hook up an old telephone, like the one we have here. And they provide voice over telephony inside of the firmware of the modem. So ISPs deploy these devices to consumers and they plug in their old telephone and they will be able to call as if it were a regular landline. Of course there's always a power connector and a little reset button for when things go really wrong. So this is the specific model we attacked during our presentation. It's the Geissler P261HNF1. There's quite some Geissler devices out there. They're all very common. So what we exported and did here will most likely work on other devices, but we didn't have access to them during testing. So it might need some adaptation in some places, but it should be pretty universal. So the basic features of such a DSL device, well, mainly routing DSL traffic, providing users with internet access. They do network address translation, so they sort of act as a firewall as well. They protect you from being attacked directly by the attackers coming from the internet. As I said, they do voice over IP telephony to provide you with phone capabilities. And as an end user, you can manage them through some local management interfaces, including HTTP and Telnet or SSH.
Okay, let's talk about a network setup you would see at people's homes. In the picture here you can see a regular network setup. It consists of one modem with several local connected devices such as a laptop or a desktop computer or maybe a server, maybe some game consoles, or perhaps a telephone. And all these devices are connected to the internet through a DSL line, which is connected from the modem to a DSLAM device on the ISP side. So, for us to have a little more flexibility to do testing with these devices, these modems, we created our test network setup, which actually contains two networks, network A and network B. And network B is not connected with a DSL line, but it's connected to the other network, to network A, through a Ethernet
cable on the one port.
On the one port, yeah, exactly. So this way we can connect to the local side of the modem in network B, from the computers locally connected to network B, but we can also connect to the remote side of the modem in network B from the computers connected in network A. And let's talk about our setup here. Because we don't have internet access, we don't have a DSL line available, we plugged out the whole internet part, and we have only one modem here instead of two. So what we did is we hooked up a server, the device you can see here, to the one port of the modem. And we also connected this laptop to the local side of the modem, and we also connected a very old telephone. So let's talk a bit about the management interfaces that are provided by the Geissler modem. Okay, the first thing we noted was a SSH management interface, which is pretty nice because, yeah, we all like to use SSH, but it's not a regular SSH interface. It's not like you get dropped into a regular bash or SH shell, but it's a special Xi shell. It's a shell created by Geissler to manage your modem. And we tried to get access to a regular bash shell by breaking out of this side shell, but that wouldn't work out. So we moved on. And there is, of course, a HTTP interface, which is the most common interface used. It's a very user-friendly interface. And it allows you to set up all sorts of things. You can set up your DSL connection, you can change your local networking settings, you can change your Wi-Fi settings, because our modem also has Wi-Fi capabilities. And it also has voice over IP functionality, so you can set up your SIP server in this interface. And it also allows you to view some basic statistics, such as bandwidth statistics. And the last thing that is provided by this interface are diagnostic functionalities. So basically you can see three different functions here, a ping or trace route function, a DSL line test, and a ring test, which basically allows you to test your internet and DSL connectivity. And the first thing, well, that looked very strange was that the output of the ping utility, when you enter a host and ping it, try to ping it, it will show the results in the text area. And it looks very familiar to the output of the Linux ping command. So we thought, okay, as a hacker, let's try to do some comment injection here. Enter a semicolon, another command, another semicolon, and see what happens. And voila.
That was easy.
That was easy. And you might notice the output of ID shows that the web server is running as root. So we can actually do everything we want with this. Okay, so what do we have? We have arbitrary command execution. The input is not filtered in any way. So there are no characters that are stripped out or anything like that. There is one restriction though. You can only enter up to 36 characters. But okay, 36 characters is quite a lot, so it's not really a restriction. And the command, as we just saw, runs as root. And we can invoke a connect back shell using this command injection. So what did we do? We created an exploit, an ugly bash script. So this bash script uses curl to authenticate against the device, and the device will set up a session, and it will return a set cookie header, so we can use that cookie for the next request. So the cookie is saved to a file. Curl provides this functionality, cookie jar, and then in the second request, we send this cookie, and we also send the command we would like to execute. So this way, we have an easy-to-use tool to execute a command from our shell on the modem. So we don't have to use our web browser, navigate to the diagnostic page, enter a semicolon, then the command, and then, yeah, it's way more complicated. So this way we can just use our shell. Okay, here you can see an example. What we did was we entered the command which is executed on the modem, and the command is nc, then our local IP port -e/sh, and this will invoke a connect back to our local computer. And it's funny because Netcat is installed by default on this device, so it was easy for us. So, and in the screenshot below, you can see that we receive a shell from the modem. And we enter a couple of commands. First one you can see, okay, we're root. The second one you can see that it's running a Linux kernel, version 2.6, pretty old one actually. So there might even be a kernel exploit available for this kernel. But yeah, we don't need that because we're already root. And in the last command output you can see that this device is based on a MIPS architecture. Okay, let's demonstrate this, because an example is cool, but we have a setup here, so we can actually demonstrate this local vulnerability.
Let's see.
Okay.
So as you can see, we can use our little dirty shell script to like this, to execute any command on the system, and I could pop a connect back shell right now, but I guess you get the idea.
Okay. So this is cool. We can use our bash script to execute commands on our device. But now we wanted to get something more persistent. So, for example, we want to just SSH into our modem and get a regular bash shell. So we thought, okay, when we SSH into our machine, we get this Zeiss shell. So how does this Zeiss shell work? Why don't we get a regular bash shell? So we opened up the passwd file, and we saw that it was actually using, the admin user was actually using a regular sh shell. So why is there a Zeiss shell and not a sh shell when we connect? It turned out that in the home folder there is a .profile file. And in this .profile file, there is an execute command which executes the Zeiss shell. So as soon as we log in, this command is executed and we're restricted to this Zeiss shell. Okay, so we thought, okay, how can we change this behavior and make it open a regular bash shell instead of this Zeiss shell? So first thing we thought of was, okay, let's remove this profile file. But it turned out that /home is mounted as read-only, so we were unable to remove any files. But luckily, the /etc directory is writable. So we changed the passwd file, and we changed the home folder of the admin user to point to the / to the root of the file system, instead of to /home/admin. So in that case, when you log in, it won't execute the profile file because it's not there. And then we have our bash shell. Okay, and then we connect using the admin user, so we don't have root access yet. And we don't know the password for root either. So we cannot just use su and get root. But there's an easy fix though, just replace the hash of the root user in the shadow file and replace it with a hash for which we know the password of, and then we can use su to get root. And we have full access. Okay, so let's wrap this up. This is a local vulnerability, so you need physical access to the local network, and you also need the credentials for the modem. So you need to be able to log in, and then you can use this vulnerability. But eventually, if you have all these things, you can get root. So that's pretty cool. Okay, so local vulnerabilities are fun. But remote vulnerabilities are way cooler. So let's talk about remote management.
Alright, let's talk about remote management for a bit. ISPs are tired of dealing with support. So what they want is a way to remotely update configurations of DSL devices and even deploy new firmware to them. So they need a way of doing that, right? So this is why someone, actually the DSL forum, invented the TR069 standard, which is a protocol which implements this functionality. So the TR069 standard implements the CWMP protocol, which stands for CPE 1 Management Protocol, and is basically used by ISPs or managing entities to deploy new configuration settings to your modem, or even provision it, or push new firmware updates. So one thing we noticed in the HTTP management interface when we wanted to forward a new port is that it said that TCP port 7676 is reserved for the TR069 connection request port. So this is also the point where we found out that TR069 exists at all. So we had to dig a bit deeper into this. What is this? So the CWMP protocol, again, CPE 1 Management Protocol, used for provisioning and configuration deployment. Basically, with the CWMP protocol, you have two entities. One is the CPE, the customer premise equipment, which basically is the DSL device in our case. And the other one is the ACS, or the auto configuration server, which is a daemon or a service running on the side of the ISP. So the ACS will initiate a connection to the CPE and authenticate itself, and then it will be able to provision new settings or roll out firmware updates. Well, now things are getting interesting, right? Wouldn't it be cool if we could push our own firmware updates to all of these modems? Because by default, the TCP port 7676 is not blocked by any firewall, so any device that can connect to it over the WAN interface. And lots of ISPs, including a big Dutch one, don't firewall anything on their side either to prevent you from connecting to this port from any arbitrary host. So let's have a look at TR069 on these Geissler modems. There's the HTTP daemon listening on TCP port 7676, like we mentioned. One thing we notice if we do an HTTP connection to this port is that in the response it will reply with a server header which says Geissler ROM page here version 4.34. More on this later. So as I said, it's accessible from any one connected host. But to do anything interesting, we require the HTTP digest authentication, which is unique to every device. So whereas we rooted our own modem, we could extract this information, but we don't have it for anyone else's modem. So that's bad. So let's have a deeper look at how TR069 is implemented on these Geissler modems. Basically, there's two binaries responsible for handling all the TR069 stuff, which are user SBIN ZyTR069 main and user SBIN ZyTR069 command. The main binary actually does most of the work, whereas the command is invoked by main to dispatch certain actions. Then there is in user lib a file called librompager.so, which is a shared object used by the main binary. This shared object actually implements all of the HTTP functionality used by the ZyTR069. So this means that ZyTR069 main implements only TR069 specific stuff, and all the HTTP and web server stuff is implemented in this library called librompager. Then there's two more files which are less interesting, but I'll cover them anyway. There's var s297 process, which is an init script for the ZTR069 daemon. So it's invoked when the modem boots, it can start the daemon, and if you pop a shell on your own modem, you can invoke it yourself to restart the daemon once it crashes. And last but not least, there's a config.xml file storing various settings.
Okay, so I will explain about the configuration file. This config.xml contains a lot of configuration properties, not only for the TR069 specific functionality, but for a lot of other stuff. But we took a snippet out of it, which are all the properties that are used by TR069, and it contains a URI to the ACS, which is used by the daemon to connect back to the ACS. And there is also a username and password in here, which are unique for every modem, by the way. So I cannot use these credentials for any other modem. And these credentials are used for the HTTP digest authentication. So as soon as the ACS will initiate a request, a connection to the modem will use these credentials to verify the authentication request. And there are a few other properties in here, but they're not really interesting. Okay, let's talk about the URLs this daemon is using. We use the string utility to get these URIs out of the binary. And the first one, the top one, is /cwmp/connection request. That's the URI that's used by the ACS to initiate a request to set up a session. And then you have a few other URIs, and they all start with /UE. And you might be wondering, okay, what's UE? What does UE stand for? Well, it turns out that UE stands for user exit. And when we open our web browser and surf to one of these URLs, it showed some basic forms. And one of the forms is displayed on the left. It's /UE/form display. And it shows a basic form which allows you to enter a text into a text box, and you can press the submit button to submit the form, and it will submit it to /UE/process form. And what will happen is process form will display the text you entered. And you could do some basic XSS or CSRF bugs or exploits with this, but it's not really interesting. But we tried some other things, and when we entered a very long string into this text box, more than 50 characters, it turned out that the daemon crashed. So we thought, okay, what's this? We're trying to reconnect, but we couldn't connect anymore. So we could effectively crash the daemon, so this is a denial of service. So this means that the internet service provider would not be able to remotely manage this device anymore. So once you reboot your modem, everything will start again and will work again. But yeah, until you do that, everything is down, and you cannot manage your modem anymore. So we thought, okay, maybe we should analyze this bug. Why is the daemon crashing? And we might be able to get arbitrary code execution.
So it was time for some quality time with my favorite interactive disassembler, IDA Pro. We managed to copy the binaries of the modem and load them into our copy of IDA Pro. And luckily there's lots of symbols inside of the binary, so it's quite easy to isolate the routines that are responsible for this crash. So it took us an evening or what, because we still had to learn MIPS as well. It was a little roadblock on the way. But eventually we managed to identify all offending routines that are related to this vulnerability. So let's have a look at the vulnerability. There's a function called handle process form, which is responsible for handling all post requests sent to this test form. This function will invoke rp get form item, where rp stands for ROM pager, by the way. So this is a routine from the lib ROM pager library. With a destination buffer on the stack, which has a fixed size of 48 bytes, I guess you can guess where this is going. So RP-get form item doesn't bother to do any bounce checking, and well, it can't because nobody is passing it a max length or whatever, so it will just start copying until it reaches a 0 byte, no byte, and then will stop, not keeping in account the size of the original destination buffer. So we're dealing with a classic stack-based buffer overflow here, the ones we all love because they're pretty deterministic and often quite easy to exploit. Let's talk a bit more about ROM-Pager first. ROM-Pager is the HTTP library made by a company called Allegro. So Allegro has some documentation online about ROM-Pager. It's a bit hard to find, but I managed to find this one manual, and it has all these examples in it which demonstrate how to implement certain actions using the ROM-Pager library. So here they are demonstrating how to retrieve a post variable, and more or less the exact same vulnerability we found earlier is demonstrated in C code right here. So at the top arrow we see they declare a character array of 25 characters, and then a bit down they invoke the RP-get form item function using this stack buffer as a destination buffer. And since RP-get form item doesn't do any bounce checking, we end up corrupting a whole bunch of the stack. So again, let's talk a bit more about ROM-Pager first. A short while ago, some genius guy, I think he did it all by himself, managed to port scan the entire internet. You might wonder, how did he do this? It's not really within the scope of this talk, but basically he compromised over 400,000 devices using default credentials. So while we're doing memory corruption here, other people are just walking into devices using admin or root. It's still possible, even in 2012. So he compromised 400,000 devices and basically built a small botnet out of it. And using this botnet, he didn't use it for evil, but for good. Namely, to port scan the entire internet. That's fun, right? So he had this little Hilbert map, XKCD style, but he also had some very detailed statistics. For example, into the most used software for various protocols. So for example, we have a page on HTTP here, and at the very top, not very surprising, we find that Apache still has the most running HTTP servers out there. But to my surprise, on the second spot we don't find Nginx or IIS, Lights 8DPD or whatever. No, we find Allegro ROM-Pager, which is apparently very widespread and has over 131 million devices connected, directly accessible from the internet. And that's only on port 80. So the ones running on 7.6 for example, are not part of this chart. So there's a lot of them out there, making up for over 18% of all public HTTP servers. I think that's a lot.
Okay, so let's talk about building a MIPS toolchain. As mentioned before, we did some static analysis on the binary using IDA Pro, but now we wanted to do some dynamic analysis. So we need a debugger to do that. And as the device is based on a MIPS architecture, we have to compile a version of GDB for the MIPS architecture. And we could do that by compiling GCC, binutils and libc from scratch and do it all manually. But there is a way more easy solution, and that is to use buildroot. So we downloaded buildroot and we compiled it, and you can then enter make menu config, and a nice menu will show up, and it will allow you to select all different things. First you have to select your target architecture, in our case MIPS, and then you can select the utilities you would like to cross-compile. And in our case we selected GDB and ltrace, strace and a few other utilities. And then it's just a matter of running make install, and buildroot will compile all these utilities for you. So we did that, and then we just had to copy over these binaries to our device, and then we could use GDB. So we ran our ZI-TR069 main binary inside GDB, as you can see here, and then we filled in the test form, as was shown before, with more than 50 characters. And then it crashed, and now we could see what was really going on. And as you can see here, the program counter is overwritten by our input. And as you might notice, there are also a few other registers that are overwritten by our input, which might come in handy later. So, let's write an exploit.
So let's talk about writing an exploit. We quickly started to minimize the buffer and find the exact position of where we were corrupting things and how we could control things. So we found out that if we send 48 characters followed by 4 bytes, these 4 bytes would control the value of PC, the program counter on MIPS. So where to go from here? I mean, we could put our shell code in the same buffer on the stack and then jump to that. But there's a little problem. On MIPS, the instruction and data caches are separated. So at the time we try to jump to it, there will be some cache incoherency, and the CPU won't actually be able to execute the instructions that came in through a data segment on the stack. So we use some basic return-oriented programming to bypass this and still be able to jump to our payload on the stack. And using this, eventually we should be able to run around code or shell code and get an interactive remote root shell from the one side. So let's talk a bit about ROP on MIPS. We're not going to cover all the basics of return-oriented programming here. There's really no time for that. But ROP on MIPS is a bit awkward. If you're used to doing ROP on x86, you know that if there's a call instruction, it will put the return address on the stack. So naturally, any subroutine will end with a ret instruction, which will pop the return address of the stack and jump there. However, on MIPS there's a dedicated return address register, which is called RA. So whenever they want to call a subroutine, they use the YOLR instruction, which means jump and link. Which will fill the RA register with the return instruction and then jump to the subroutine. So at the end of the subroutine, there's a jump instruction to the RA register, which will return. So on x86 we can have a nice slide with return addresses and just execute them in order. But on MIPS we need to be more careful, and sometimes we need to fill the RA register ourselves, or rely on gadgets that aren't at the end of the subroutine, but somewhere in the middle. So then we still need to bypass the separated instruction and data caches. One way to do this is to force a context switch. An easy way to force a context switch is by invoking some routine that takes some time to give the OS time to do a context switch. For example, sleep. So we will be returning to sleep with an argument of 1, so there will be a second delay. So it's time to synchronize, and then our code is actually visible for the CPU and it can be executed. Luckily the stack on this device is executable, so we only need a really minimal ROP chain to deal with the cache incoherency, set up a pointer to our shell code and eventually branch there. And there's no address space randomization either, so it makes things kind of cheesy, but it's still a hostile device. On the CPU architecture we don't really know yet, so there's a bit of a challenge. One important last thing to note is that on MIPS, whenever a branch is taken, the instruction after the branch is always executed before the branch. So regardless of whether the branch is taken or not, the instruction after that will always be executed first. This is something to do with pipelining, but we won't get into that right now. So let's talk a bit about the gadgets we used and how creative we got. I mean, there's multiple routes to success, and this is probably not the easiest or cleanest way, but it worked for us as MIPS newbies. So gadget 1 will set up the A0 register with 1, which is the argument for sleep. Then it will fill T9 with the contents of S1. And during the GDB screen in the slide earlier, you noticed that we controlled a bunch of more registers as well, including S1. So we fill S1 with the address of gadget 2. So now gadget 2 is being executed. But this is a bit of a special gadget, because at the end of this gadget it will jump to T9, which at the start is filled with S1. So at the start of gadget 2, S1 still contains its own address of gadget 2, So naturally, once it goes through this gadget, it will invoke gadget 2 again. But in the middle of this gadget, there's a couple of load instructions which load various values from the stack, amongst which are RA, S2, S1 and S0. So, and we control the stack as well. So the first time it runs through this gadget, S1 will be filled with the address of sleep, which we get from the stack. And then it will execute gadget 2 again, but this time S1 contains the address of sleep. So by the time it gets to the end of this gadget, it will actually execute sleep and not execute itself again and again and again. But during the second time this gadget run, we also loaded some new values from the stack, including a value into the RA register. So when sleep is done, it will return to this function. So we fill it with the address of gadget 3. In gadget 3, we load a bunch of more values from the stack. Basically, we set up the RA register to contain the address of gadget 4, S1 to contain the address of gadget 5, and then we reach a jump instruction, which will jump to RA. So we now reach gadget 4. At gadget 4, we put S1 into T9. So T9 now contains the address of gadget 5, and we jump to gadget 5. But before we jump to gadget 5, as I mentioned previously, any instruction after a branch will be executed first. So the last instruction of gadget 4 is an add integer unsigned instruction, which will fill the A1 register with the value of SP incremented by 184. So by the time we arrive in gadget 5, it will put this value of A1 into T9. So now we have a pointer relative from the current stack pointer where we can put our shellcode at a fixed position. So this is nice. We don't need to guess any addresses on the stack. We do it all using ROP. So eventually we'll reach the jump instruction of gadget 5, and this will actually execute our shellcode successfully now. I guess it's time to pop a shell. Let's see if this works. The demo gods have not been on our side lately.
Okay, so now we connect to this box over here, which is connected to the one port on the modem, so it's be able to connect to the remote side of the modem. And we'll start a listener. We wrote our exploit in Python, by the way. 1.154 7676. Yes.
So I really hope this will work, and it might take a while because we're kind of sort of simulating an internet here. It worked the first time. So there we go. We just popped a shell from the one side. It might have been a bit fuzzy to you as we were using all 192.168 whatever addresses. But this is because of our complicated network setup here. So we're actually coming in through the one port right now, which is Ethernet, but it works just fine using the DSL line as well. It's exactly the same service running there. So now we successfully popped a remote shell on a device. And theoretically, we could do this on any device that it has port 7676 open on the internet. So again, we can quickly see the CPU info. It's actually a MIPS device. Yada yada yada. Okay, let's see.
Okay, so you can imagine this is a very serious vulnerability because port 7676 can be reached from any IP address. It's not firewalled, and so we thought, okay, we should do something with this. Maybe we should contact Geissler, which created this modem, but it's an Asian company, and we're not paying them, so we were not sure if that was going to work out. So we thought, okay, maybe it's better to contact our internet service provider. So that's what we did. We contacted KPN, the KPN CERT team. Okay.
KPN CERT rolled out the new firmware. We went there for a little meeting to discuss with them the scope of these vulnerabilities and well, how we exploited them and how they could possibly mitigate them. Of course, they were quite shocked by what we found. By any chance, is there anyone of KPN in the room right now? I see a couple of hands over there. Guys, come on stage.
Yeah.
It's great to have you here. Give them a round of applause.
On behalf of KPN, I'd like to thank you for hacking our network and making it better.
It's okay, it's okay, it's a pleasure.
We'd also like to give you these shirts, which say, I hacked KPN, and all I got was this lousy t-shirt.
Ah, sure, man. Nice. How nice of you. Thank you, thank you.
It's great.
Thanks a lot.
Thank you.
It's good to have you here. Thank you, thanks.
Thank you.
Thanks.
Responsible disclosure works.
Yeah, sometimes it does. So as you can see, everybody is very happy. The customers are happy, we are happy, we won't be getting sued, people are safe, KPN is happy, everybody is happy. So much happiness around here.
It's great.
So, now to more serious things. Let's build some Trojans or spyware for DSL modems, or look at how we could do this. So first of all, I started off by cross-compiling libpcap for MIPS, because libpcap is very handy when you want to build your own toy sniffers or compile TCP dump or whatever. So I started by building a small utility which I call the tube miner, because it mines your tubes. So basically you can run this utility on your modem and it will look for any HTTP traffic that's being initiated from both sides. And it will give you it will do a small protocol inspection and show you what pages the user is visiting. Maybe he's browsing his email, I don't know, surfing some porn or whatever, doing his taxes. We can all follow in real time now, so that's quite nice. I wanted to include a little screenshot of the utility here, but we didn't get time to do that. I'm sorry, we won't be demoing it either. However, another thing we focused a bit on, since these things do voice over IP telephony, and it's quite a common feature of these things, lots of people buy all-in-one internet access with telephony, TV, and internet in one box, and it's basically that then. So they just hook up their phone there and use it as if it were a regular landline. So we started looking a bit into how we can intercept these voice calls, right? So I had built libpcap, and I already started wasting a couple of evenings trying to figure out how to follow the SIP protocol, notice when there is an RTMP stream being established, because at that point it switches over to UDP, so then you need to start following the UDP stream. From the UDP stream you can extract the encoded audio samples, which are often encoded as ULAW or ALAW, or GSM codec. And then we can grab those and hopefully reassemble an audio file and play them back. This turned out to be quite some rocket science. Luckily, someone else had already done this rocket science back in 2005, and this guy wrote a utility called VoIPong. VoIPong basically does what I just described. So it is following SIP connections on TCP, and whenever it notices that that it will establish an RTMP stream, it will quickly switch over to sniffing UDP, and it will start capturing the RTMP stream. It will decode the samples to PCM. It will write these files to the disk, and when it's done, it will invoke the SOX utility to actually convert these raw PCM streams to a WAV file, common WAV format. However, this is not really practical on an embedded device such as a DSL modem, where we have almost no free disk space, so we cannot really write these files to disk. VoIPong does quite a lot of logging. It requires some configuration, so we started by ripping out the logging. We ripped out the part where it writes files to disk, and instead we relay all the information that was normally written to disk using a simple protocol to a client running on the hacker's machine. So the hacker can in real time capture the audio stream of the telephone call. And after that, on the client client side of the hacker, it will reassemble these packets into a waveform. So we are going to try and demonstrate this right now. I really hope it will work, because this is...
Yeah, so this telephone over here is connected to our modem, and normally it would be connected to the SIP server of the ISP, and you would be able to call any phone number, but because we don't have internet access here, what we did is we set up our own VoIP server on this box. It's an asterisk daemon, and we're now gonna sort of simulate a call and see if we can catch it and play it back. Okay.
Wait, no, you cannot start yet.
Okay.
I messed up. Give me a couple of minutes.
Yeah, sure.
So in all my hurry this morning, I've actually forgot to copy over these files in advance, which is kind of a big deal because we're running out of time here. So let's see if I can quickly fix that. I love Python. Oh, sometimes I don't. So why is this not working? Should be working. Oh, I see. Not very good with computer. So slow for a local area network.
There it is.
Okay, so now give me a couple more moments. Yep. Is this it? Yeah. So we start this, and
Okay, ready?
so let's try it out.
Okay. Hi, this is Steven. Hey, I'm great. I'm at Hack in the Box right now. Yeah, you're right. I'm on stage now, talking about DSL devices. Oh, don't worry, it's okay. Oh no, I haven't checked yet.
This one lengthy phone call.
Okay, I got a secret code. Thanks. Thank you very much. Bye.
So right now, VoIP is still taking its time to actually determine whether the call is over, because UDP is stateless. So it just has a little timeout where it waits for the RTMP stream to stop transmitting anything from both sides, and then it decides the phone call is over. So now you'll see that my script on the hacker computer here received a bunch of data, and hopefully it will have reassembled a audio file. Final.final. Okay.
Hi, Peter speaking. Hi, this is Steven. Hey, Steven! How are you doing, old friend?
It's a really low quality call.
Hey, I'm great. I'm at Hack in the Box right now. That's amazing. You mean Hack in the Box in Amsterdam, right? Yeah, you're right. I'm on stage now, talking about DSL devices. Oh, I'm sorry to interrupt you then.
Oh, don't worry.
One last thing. Did you get my email yet?
Oh no, I haven't checked it.
Oh, okay. Well, once you receive it, the secret code is 31337.
Okay, I got a secret code.
Okay, that's it. Have a wonderful day, Steven.
Thank you very much.
Bye.
Okay, as you can hear, there were some timing issues and the quality is not that good, but well, you could hear it, so.
We can blame the quality on the quality of these phone codecs. They're really low, they're only needed for voice. And yeah, we had lots of fun scripting out this little scenario last night because we have a little asterisk VoIP daemon running on the server here because we couldn't easily connect to the internet here, so that was the most easiest way. And we had to draft this little role play, and I had to speak it into a WAV file, record it, put it on the asterisk box, time it a bit. So that was a bit hairy, but I'm glad it worked. So, of course, there's tons of more fun we could be having with these types of devices and this kind of access. For this presentation, we didn't really focus on command and control or like building a huge botnet, mostly because we were well out of time. But in the end, it's just Linux. So any trick that will work on Linux will work here as well, as long as you keep in mind the constraints of these types of devices. So they have a limited memory, limited CPU, but they are great at doing network stuff. They come with IP tables out of the box almost all the time. So there's lots of fun to be had there. We can reroute packets, drop packets, forward packets to a squid proxy, get creative. Using libpcap, we can write our own low memory, low CPU, custom sniffer software that is tailored for specific needs. I kind of tried getting SSL strip to run on the modem, but SSL strip relies on Python and is quite hungry, uses lots of external modules, so I might be able to get it to work given more time, but we didn't do it right now. Some other things that popped to mind, of course you could build a huge modem botnet out of this, and what is great about a modem botnet is that it's persistent in the sense that people will probably start noticing that their internet connection is lagging, so they will reinstall every single computer in their home, but it won't make a difference because the modem is the device that is infected. They can reset the modem, but if you craft the malware properly, it will still be there after a reset. And so in a sense, it's a really persistent way of backdooring a network. And of course it doesn't just work at modems, you can attack switches, routers. These devices are getting more complicated and complicated. So they usually run some form of Linux, which is very familiar to us hackers, so it's a great thing to attack. Another thing that you could do is, since they are using VoIP a lot on these types of devices, you could make expensive outbound calls to, I don't know, payphones and monetize it that way. So, I lied, we did build a botnet. Over 130 million nodes. I'm just kidding, but you can start bidding right now. Let's start wrapping this up. Consumer DSL devices, or well, network devices in general, are a very viable target to us hackers. We should not be afraid of unknown architectures, obscure software, or undocumented software. And I think more research should be done on these types of devices. I mean, I'm not saying nobody is doing research on them, there's lots of people doing research on them, but as you saw, old school classic vulnerabilities, really basic stuff like shell command injection and really simple buffer overflows are still alive and kicking at this day, at this hour, in these types of devices all around the world. So more focus on the security of these types of devices is necessary. And like I said, nothing will stop a hacker, so different architecture, weird file formats, a low power CPU, nothing will stop us, we will always find a way. I thank you for your attention. Are there any questions? Oh, also we will publish all of our exploit code and tool code on GitHub. Give me 1 or 2 days to actually prepare the repository and put it up. The code is a big fucking mess right now because we're in a hurry to get this working for the presentation here today. Yep.
We've got a question over there.
So hi. So maybe it's more a question for KPN people, but usually what you do when you have a DSL modem and you want to administrate it is set up a second ATM virtual circuit and basically a private one and run your interface over it. So isn't that a way to mitigate this kind of flow and not having any port reachable from the internet line?
Sorry, I'm not sure if I entirely got the question. You were saying it might be possible to mitigate these types of vulnerabilities.
So basically it's a DSL modem. So you set up ATM virtual circuits to the ISP to exchange your data. And usually on a DSL modem, you can set up different virtual circuits at the same time. So you could have a virtual circuit for your internet line and a virtual circuit for administrating the modem remotely, making this daemon non-reachable from the internet.
Right.
Period.
Right. So there's definitely tons of ways to mitigate this, both at the ISP side, but also on the modem side. I mean, the modem comes with IP tables, so they could put it inside of the firmware. But I'm not really a network specialist, but I'm sure they could do something to mitigate it at the ISP side as well, which is more or less what our ISP KPN did to mitigate this issue very successfully.
Yeah, but please note that we focused on consumer DSL devices. So these devices are delivered to their homes, installed, and nothing is done with them. So
Yeah, nobody really bothers to touch them. They just plug and play or pray.
exactly.
Okay, any other questions? No, in front.
So, assuming someone has tried these two methods, do you have any other ideas on how you can get in a router?
Sorry, what was it?
Do you have any other ideas apart from these two methods on how can you get inside a router?
From the remote side, you mean?
Even from the local one?
There are possible other vulnerabilities which you could use to gain access for the local side. For the remote side, there should be a service available from the remote side.
Yeah, so there is some attack surface that you need in order to attack these types of devices. And we got lucky with the TCP 7676. Basically, if there's nothing open from the outside, that more or less means you're fucked, unless there's like a really low-level bugs in TCP implementation or whatever running on the box, but there's Linux. So it's pretty solid in that sense. There might be configuration issues in there which might allow you to do something, but if there's no accessible services from the outside, it's going to be a hard job breaking into that modem. Well, of course, we discussed earlier the local vulnerability, and we could do a cross-site scripting attack. So we could leverage a cross-site scripting attack to execute a cross-site request forgery attack. So we could lure someone to a web page where we make them attack their own modem in order to open a port remotely so we can connect back to that. So there's multiple ways to do that, but usually having an outside-facing service on the internet side that we can attack directly is of course the best for us hackers. We don't need, I don't need to convince my friend Steven here to visit a stupid web page so that he will attack his own modem. We can just attack anyone without any consent at all.
Yeah, but that didn't even work. The website link didn't even work either.
I'm not sure I understand.
I've tried this third method as well, the request forgery, but it didn't work either.
You've tried what exactly?
Wait, do you mean this URL or the?
No, get someone visit the website and then open
Yeah.
a port on the router. That didn't work either.
Okay, well, I don't know. Depends on what router, what device, what types of vulnerability might have been plugged already. Thank you for your question.
All right, I think we're just about out of time. So besides thanking you for a great talk, much respect for putting up the demo, guys. Thank you.
Thank you.
Thank you.